So today we shall be looking at this question: minimum number of vertices to reach all nodes. So the question says that we're given a directed acyclic graph with n vertices numbered from 0 to n minus 1 and an array edges where the edge from 2 represent a directed edge from to node 2. So we have to find the smallest set of vertices from which all nodes in the graph are reachable. It's guaranteed that a unique solution exists. Notice that you can return the vertices in any order. So for instance, here we have 6 nodes and these are the edges. So directed edge, you can see 0, 1 and 0, 2, 2, 5, 3, 4, and we should have 4, 2. So the answer is 0 and 3. That's the smallest set of vertices from which all nodes in the graph are reachable. So one thing you will see here is that the answer for 0 and 3 only have outgoing edges. They don't have any incoming edges. So that gives us an intuition that any node that has an incoming edge cannot be part of the output. So it's possible to reach all the nodes from a single vertex. It's not possible. So from 0 we can reach 1, 2, 5, and from 3 we can reach 4, 2, 5. Okay. So here you will see similar thing. The output is just those that don't have any incoming edge: 0, 3, 2, and 4. So 0, 3, and 2. So 4 is not there because that's an incoming edge. Alright, so n minimum of 2, the values from 0, the length is guaranteed to just be 2 of each element. The length of the edge can be 1, so we can have just 1 in the edges, just 1 element. So there can be an empty edge, so there must be at least 1 edge. Okay, so we really don't have a base case there. N is 2, so that's the length of the number of nodes there. So we're guaranteed that we can have at least minimum of 2, and it ranges from 0 to like here where n is 5, so it starts from 0 to 4. All right, so how do we approach this problem? It's simple. For us, we can just see that anything that is occurring at this second part of the indices cannot be part of the solution. That is clear. So that means that once we just take anything that is in the second part of these indices out, then we can guarantee that whatever is left will be the solution. All right, so as we look at here too, say 1 cannot be part of the solution, and 4 cannot be part of the solution. Okay, so we know that the solution will lie between the ones that are actually here. So you have 0, so we have 2, we have 3, but it's possible we have something here like 1 here, so we cannot use the first index since it's possible to have something that cannot be part of the solution here. but we guarantee that anything that is here on the second index cannot be part of the output. So we can use that knowledge to devise a solution. All right, so first let's get all the lists. So because we have a large number, we'll be using set. So let's get all the nodes. So these are our nodes, and it's going to be in the range of n, and we will make that to be a set, and that's going to run from 0 to the number before n. Then the next thing we want to do is our output. Okay, let's say we call this our output. So we call this our output. Now we can now say the nodes that will be excluded. So node excluded from the result, we can make that a set as well. So we now go to for edge in edges, and we can add nodes. Let's go excluded. We can add the second part of that edge, which is can you say 1? That will be at index 1. So we're guaranteed that we always have this will always be 2, so each element will just be 2, so 0 and 1. So we're guaranteed we won't have an error here. Okay, so once we have that, so we know these nodes that are excluded will be populated. So what we now need to return is actually the output minus the nodes that we have excluded. So because it's a set, it will give us what we need. So they want us to return a list, so we can just convert this one back to a list since it's a set. Yeah, I think that's all we need. So let's try run the program with some example and see whether it makes sense. So here our n is equals to 6. So our n is 6, and so what we do is our edges. So our n is 6. So our output is going to be a set of 0, 1, 2, 3, 4, 5. 6 will not be included. So this will be initially empty. So for edge in edges, so the first one will be 0 and 1. So we are adding the second index, so we add 1. Then the next one we add 2. The next one we add 5. The next one we add 4. The next one we add 2. Okay, so because we are using a set, this duplicate will be taken care of. So what we now do, by the time we get here, we now remove the ones that are here from this place. So 1, 2, 5, 4 we go, so we have 0 and 1, and we just turn this to a list. Oh sorry, we have 0 and 3, so we just turn this to a list. So it's 1, 2, 5, 4 will not be included. So that's correct for this. Let's look at this as well quickly. So by the time we come in here, our n is still 5, so this still remains. The set that will be excluded will be 1, another 1, another 1, 4, and another 4. But because we are using a set, so all these duplicates will not be included. 1, 1, 4. So we can now take 1 and 4. Is that correct? 0, 1, 2, 1, 3, 1, 1, 4, 2, 4. Okay. So we take away the 1 and still 1, 4. So if we take away 1 and 4, what will be left? We have 0, we have 2, we have 3, then we have 5. Oh, something is wrong. Our n is 5, so this will stop at 4. So we don't have 5 in our list. So that's also correct. So we have 0, 2, 3. So let's run that. And then let's look at this other one too. That's correct. So when we have 5, and let's run this. Okay. That's also correct. So let's submit and see for everything if that works for all possible scenarios. Good. All right, so that works. Okay, thank you very much, and see you in the next one.